All right, greetings and welcome, friends. We're taking a look at really our first true algebra lesson for Algebra 1. The name of this lesson is Solving One-Step Equations, really is what it is. And in order to do so, I'm going to give you a handful, 4 of them, I guess, so you're missing a finger, of properties that will allow us to solve equations efficiently. Now, the problems I show you today, you probably could guess the solution of some of these. I'm less interested in the answer than I am the procedure because, let me tell you, and I've seen this plenty of times, I've been teaching math for over a decade, I need you to know this process of how to solve algebraically. Because when the problems are easy, yeah, sure, you can guess. But if you just guess and don't learn the process, when the problems get hard, you will have no strategy to fall back on. So I'm intentionally giving you easier problems right now as you learn a new skill in solving those problems. So please do not sabotage your future self by ignoring the process, because it's all about the process. So here we go. So here's a core concept. The addition property of equality is the name of this, where it says this: adding the same number to each side of an equation produces an equivalent equation. So it says if A equals B, then adding C to both sides of that equation results in the same thing. Imagine if I have a scale, right? Here's my sad little balance beam scale. And if this scale is balanced at this point, let's say there's like, I don't know, 2 green circles and like an orange triangle over here. And let's say I want to add, if it's balanced, so that means 1 orange triangle is the same weight of 2 green squares. If I add a blue triangle to both sides, do you think it will still be balanced? The answer is yes. As long as I add 2 objects of the same weight to both sides, it will maintain its equality. It will maintain its balance. And the same thing is true with the subtraction property. Subtracting the same number from each side of an equation produces an equivalent equation. So if A equals B and I subtract C from both sides, it will still be equal. The equality was not broken by doing that. So if I had the same scale balanced and I subtract a blue diamond from each side, it will still be equal. All right, so that's the big idea for addition and subtraction properties of equality. So that's what we do. So let's jump right into some examples now. So here we go. Here's an algebraic equation. It's a relationship between these two sides. And when I ask you to solve an equation, what I'm asking you to do is to tell me what number for x makes this equation true. All right, and you might be able to guess that, like I said. All right, but I'm not interested in your ability to guess the answer quickly. I want you to learn the process. So here we go. I've got x minus 3 equals negative 5. And if I want to solve for x, when I solve, another way mathematicians refer to this is to isolate the variable. I want to get something where in the end it says x equals something. All right, so I want to get x by itself. And in order to get x by itself, I've got to get this minus 3, this subtract 3, away from it. And in order to do that, I'm going to have to move it. And the only way I can cancel out subtracting 3, what do you think the opposite of subtracting 3 is? Thoughts? What's the opposite of subtracting 3? What would undo that? Silence. The opposite of subtracting 3 would be to add 3. And I can't just add 3 to this left-hand side of the equation. I have to do it to both sides, because if I don't add it to both sides of that balance beam, remember, if I don't add it to both sides, it will no longer be balanced. It'll lose its balance. So adding 3 to both sides, notice what I get. It still is equal. The minus 3 and plus 3 cancel out. I get x And when we do our work, we work vertically, just so you're aware. So if you've been in the habit of working horizontally, right, sideways, train yourself out of that. And we write our equals signs vertically underneath each other. So x equals, and -5 plus 3, you guys are now experts on that idea. The signs are different, so I subtract the numbers. 5 minus 3 is 2. And the more influential one was the 5, so I take the sign of the negative. So I get x equals -2. Now it asked me to justify my step. So that means I can't just I don't know, I just added 3. I need to give a reason as to why that's true, because your logic has to be sound. You have to be able to verify and justify what worked. So the reason I was able to do this was the addition property of equality. All right, that's what allowed me to add 3 to both sides and have that work. Now check out this next example. Here I've got the y on the right-hand side. That's not a problem. All right, that's not a problem. We're fine with that. If I want to solve for y, I'm looking for the number that when I plug it in for y makes this equation true. So that's what I want. When is y, what value of y will make the equation true? So to get y by itself, I have to get rid of this plus 2.8. And what is the opposite? What is the inverse of adding 2.8? How can I undo adding 2.8? Come on, let's get some guesses here, friends. What's the opposite of adding 2.8? Subtracting 2.8. Perfect. So that would cancel out, but in order to do that, I also have to subtract it from this side, right? I have to do it to both sides of the equation, all right? The equal part is the balance piece. So I'm going to get equals to y. These cancel out, right? Fruit Ninja style. Those just swipe, swipe. And now I've got -2.8 plus positive 0.9. Same issue as over here. So I'm going to subtract those numbers. 2.8 minus 9, I believe, is 1.9. And is it going to be positive or negative, do you guys think? Negative, because 2.8 was more influential than positive 0.9. Now, it's kind of weird to say -1.9 equals y. Whenever I solve an equation, I like to have the variable on the left-hand side. So if -1.9 equals y, do you think it's also true that y equals -1.9? Does that make sense? Yeah, I mean, equality works both ways there. So let's justify this step. So this step that I was able to subtract from both sides was the subtraction property of equality, right? All right, so that's what allowed that. Does anyone know why I was able to flip this around like that? I mean, hopefully you believe it to be true. It's called the reflexive property of equality. I know we haven't covered that one. But basically what the reflexive property of equality says is if A equals B, then B equals A. It's true both ways. Now, just to verify this for you even further, it's possible to do what we call a check, where if x is really equal to -2, that means I should be able to plug a -2 into the original equation and just do regular PEMDAS and come out with a true statement. So let me just do a check here. So when I plug -2 in for x, it's a good idea when you substitute to use parentheses here. -2 minus 3, is that equal to -5? -2 minus -3, -5 equals -5. Guys, I think that checks out. Cha-ching, check it, check it. And let's even try this other one. Let's just do a check here, which I usually just write CK when I do a check. So if y is equal to -1.9, I plug it into the original equation for y. Okay, so the question is 0.9 equal to -1.9 plus 2.8? Yikes. So let's see, 0.9 on this side. 2.8 minus 1 would have been 1.8. And then minus 0.9 from 1.8 is going to be positive 0.9. So it does in fact work out when I use the PEMDAS here. So when solving these, I realize you might have been able to just look at this and have been like, what minus 3 is negative 5? And maybe you could guess that. I'm not interested at all in your ability to do that right now. Right? That's like a cool trick. That's good to know. You could use it to kind of check your answer. But I need you to learn these properties of equality and how to add and subtract from both sides. Let's see, how am I doing for time? I'm going to skip past this next part and give you two more properties. Two more properties. Here we go. Which will hopefully make just as much sense. Let's see. We've still got a few minutes. All right, so this is the multiplication property of equality. Notice it's the same idea. If A equals B, then I could multiply both sides by the same number, and they'll still be equal. And they just have this extra little rule. They say, hey, don't let C equal 0. Technically, both sides would still be equal. It just wouldn't be very interesting. And then there's the division property of equality. If A equals B, then I can divide both sides by C, right? And it will still be equal. Still be equal. So, and here there's a rule, once again, that says C cannot equal 0. And the reason that is the case is because, I don't know if you guys realize this, but it's illegal to divide by 0. You'd end up with undefined. I don't know if you remember that from back in the day. Maybe not. That's fine. But let's try to put these properties to use. And if we run out of time, if the bell rings, you guys can head out. I'm just going to keep recording this video by myself anyway. And the homework, you know where it is. I don't actually. I'm not good. Yeah, let's see. Come on in. Come find a seat. So let's see. So here's an equation. Negative n divided by 5 is equal to negative 3. So Austin, if I want to solve it, it's currently being divided by negative 5. And so what I can do is multiply both sides by negative 5. Multiplication is the inverse operation or the opposite of division. And notice what happens here. When I multiply, the 5s would cancel out. The minus signs will cancel out. And what do I get? I get n by itself. The variable is isolated, which is what I wanted. N equals, negative times a negative is positive. 3 times 5 is 15. And the property I used is the multiplication property of equality. All right, this one looks scary. All right, I want to solve for x. Does anyone know what this symbol is? That's pi, right? That's approximately 3.14159. X is being multiplied by pi. What is the opposite of multiplying by pi, do you think? Yeah, divide both sides by pi. Pi is just a number, so I can divide both sides by pi. And let's see what cancels out here. Notice the pi's, ching, ching. And here, oh, these pi's also cancel out. Yeah, you guys can head out. Have a great day. And I'm going to get x equals negative 2. X equals negative 2. And I did that using the division property of equality. I was able to divide both sides by pi, and it maintains its equality. Let's see, last little example here. Z is being multiplied by 1.3. The inverse operation of multiplication, the opposite of multiplying, is dividing. So I'm going to divide both sides by 1.3. Ooh, wow, this one's some tricky decimals here. The 1.3's cancel out. I'll get z by itself. Bye-bye. Equal sign. And 5.2 divided by 1.3. If you wanted, you could actually shift those decimals. 52 divided by 13. If I shift both of them by one place. And 52 divided by 13, if you're a poker player, you know that there's 52 cards. Divided by 13 cards per suit gives you 4 suits of cards. And so that's how we solve these. We're using inverse operations. We're undoing the thing that was happening to the variable. All right, so we're undoing the thing that was happening to the variable. So if it was something was being added to it, I get it by itself by subtracting. If something was being multiplied by it, I get it by itself by dividing. All right, so thanks for watching, internet friends. Hopefully you have a great day. Bye-bye.